Greetings, viewer. This is the official presentation submission for the team Matsya for the problem statement 1658. The problem statement title is Development of a Versatile and a Fast Algorithm for Optimal Ship Routing. Now, so our proposed solution is that we will build a adaptive ship routing algorithm designed to minimize maritime routes by minimizing fuel consumption. We will integrate Dijkstra's algorithm and reinforcement learning to make real-time decisions for dynamic weather adapting and collision avoidance and several other things. Dijkstra's algorithm will be our baseline for this reinforcement learning model. We will use a interface which will make it easy for the user to understand by using topographic visualization. We will mark the areas with bad weather and unsafe sea conditions in red, and the most fuel efficient time optimized route will be marked in yellow, and the green more comfortable route will be marked as a green circle. So if we click on this image, I believe we can see how this will be done. And the uniqueness of our solution is a hybrid approach by using Dijkstra's algorithm with reinforcement learning and topographic visualization for intuitive decision making, so that the user can have a much more degree of control over this app or this particular program. And it will also contain real-time dynamic routing, which will it'll help with sudden changes in the sea conditions, sudden changes in the weather, and this system will not be dependent on static data like traditional systems are. And so this here is a flowchart. So the user will input source and destination. The calculation of the possible fastest, optimum, and safest routes will take place. If the choice of route is the safest, the information is stored to the cache, so that there is to basically have a lot of memory optimization. Then the data will pass through collision avoidance system. Then we display the route, and then we stop the program. If the choice of route is optimal, which means it can be either on the yellow or orange range and or on the green range. So the green range is the same as the safest. For the orange, we go towards the backend that is controlled by the Node.js, which will fetch API data from several programs or several websites all throughout the net, and it will make a dynamic route like we can see over here. If the choice of route is the fastest but it is red, our choice of route gets dismissed, the program stops, and then we go back to choosing the choice of route. If it is it is orange, or if it is green, then we follow the previously mentioned paths. Now we have our technical approach slide. The technologies that we'll be using in this particular project will be basically it will be upon TensorFlow for the reinforcement learning models. For training this model, we'll be using Simulink or MATLAB based any some simulation software. For the backend, we'll be using Node, Express, and Spring JS. For a Node for optimum API fetching, Spring for management of the entire program, for fast requests among or between the components of the program, and Express for fetching data from the database. And the methodology is it is based upon four factors: data collection, algorithm development, visualization, and testing and refinement. Data collection will be done by weather APIs and ocean current data APIs and map APIs. Algorithm development, we have used Dijkstra's for the baseline, and then we'll be training a reinforcement learning model. Visualization, we'll use several types of libraries for visualization like Seaborn, OpenCMap, and then we'll be focusing on testing and refinement of our whole project. Now, this is the server side and client side architecture. You can see on the client side there is only the user interface. There will be the HTTP requests that will be sent to the API gateway. Then we have the visualizations, and on the server side there'll be a database which will also hold the cache of the currently running program for the memory optimization. And then we have the API gateways. Now, the feasibility and viability analysis of our program. So there are several constraints that we have, which will be collision avoidance for certain unmapped sections of the sea, and then we'll have network problems. The potential challenges that we have are data inaccuracy or sudden environment changes, technical integration issues, and we will also need low latency on our network to make quick decisions. We have several strategies to overcome these challenges. Some of them are listed over here, as we can use multiple sources for data accuracy. We can use regular updates for the legal compliance part of the program. We can have adaptive algorithms for this routing that we are trying to build actually. And then yeah, so that's that. The impacts of such a solution that we can build is absolutely profound. Um, this model, based upon our research and on similar models, can reduce the fuel consumption by 5 to 10% depending on the weather conditions, vessel type, and accuracy of the weather forecasts, which can lead to around $20,000 to $40,000 of fuel fuel costs that are saved in general. And we will also have safer voyages for the seafarers and our merchants. Then there are several benefits for such a solution. Yeah, so these are our research and references. Thank you for staying with us. Thank you for listening.